The next unit we're going to take a look at is lines. While we've all seen lines before, the techniques that we've learned in the past were only useful for graphing things in 2 dimensions. Now we're going to apply the vector techniques that we've learned so far in this course in order to figure out ways that we can graph things in any dimension we want. In order to do this, we need 2 pieces of information. We need first a direction vector and a position vector. Let's take a look. If we wanted to graph the line here, r of t, we would need a position vector to give us a point on the line, and then a direction vector which is going to tell us which way the line is going. You'll notice that if we take a point that's on the line and add some scalar times this direction vector, we'll always end up on this line. We have multiple definitions for equations for a line. Let's take a look at our first. The vector form, which will probably be the most typical form that we use, will be r of t plus p, our position vector, plus t times d, our direction vector. The next form of equation that we can take a look at is our symmetric form. It's going to be x minus x naught over a. Well, let's take a look at what each of these components are. These x naught, y naught, and z naught correspond to x, y, and z of the position vector, and these a, b, and c correspond to the x, y, and z components in the direction vector. An expression for each point on the line, and each point has an x, y, and z component. We can write a parametric equation for each. We can write an equation for the x component, an equation for the y component, and for the z component. In each case, the x component would be equal to the x point of the position vector plus the t times the x component of the direction vector. Let's take a look at how we could apply this. As in the past, we can, given any 2 points, we can uniquely define a line between them. First, the first thing we need is a direction vector. In order to get a direction vector from 2 points, if we take a minus b, this will give us the vector in the direction from b to a. If we subtract each of these, we'll get the vector 1 minus 1, 1. Subbing this into the equation that we had before, we first need a position vector. Conveniently, the position vector that we're interested in could be any point that's on the line. We happen to know 2. In this case, I've selected point A. Writing this out in the vector form that we stated above, we end up with r of t is equal to 2, 3, 1 plus t times 1 minus 1, 1. Let's talk about how we can take the vector form equation and put it into the other forms. As I said before, we can think about the vector equation as being an expression for each point on the line. Each point on the line has an x, y, and z component. If we equate the left-hand side with each of the components on the right-hand side, we can come up with the parametric equations. For instance, the x component of the answer will be equal to the x component from the position vector plus our parameter, t, times the x component of the direction vector. We end up with this expression. We can repeat this process for the y and z components to end up with the parametric equation. From here, we can easily come up with the symmetric equation. Where this equation comes from is taking the parameter t in each of these components, isolate it, and then setting them equal to each other. For instance, if I isolate t in the first equation, I end up with x minus 2 over 1. We can do the same thing for this one and end up with 3 minus y is equal to t. And setting these equal to each other, we end up with these 2 equations. Now, I didn't have to leave the 1 in there, but as you may know, this value will not always be 1, and I wanted to specify the form that I listed above. Get used to switching between these forms and using them interchangeably, as some problems will lend itself to being easier depending on what form you use. Next, let's take a look at an example of solving the intersection between 2 lines. Equation 1, r1 of t is equal to 1, 0, 1 plus t times 1, 1, negative 1, and r2 of s, which will be 2, 3, 4 plus s times 0 minus 1, 2. So the first thing we want to recognize is if 2 lines are intersecting, then it means that their x, y, and z components need to be equal. Following this logic, let's write each of these equations in their parametric form, yielding the first 3 equations for r1 and the second set of 3 for r2. As we said, we want their x, y, and z components to be equal, so we can come up with a new set of equations by setting them equal one at a time. If you set the first equation for x equal to the other equation, we can come up with equation 1 here. 1 plus t is equal to 2 plus 0s. We can repeat this process for the y component and the z component, and we now have a system of 3 equations and 2 unknowns. As we all already know, we can solve a system like this by picking any 2 of these equations, subbing one into the other, or using elimination. In this case, it'll be easiest for us to solve this system by choosing equation 1 and solving for t, as the result is immediate, taking that result, subbing it into equation 2, and yielding a result for s. We end up with parameters t is equal to 1 and s is equal to 2. What this should mean is if we subbed t back into equation 1 and s into equation 2, we should end up with all 3 components being equal. However, we need to check. We haven't used equation 3 yet. If we sub these values into equation 3, we see in fact that these are not equal. What this tells us is that these lines are skewed. It means that they intersect on 2 of the components, but they miss on the 3rd. Just like in 2 dimensions, we can end up with different solution types. We can have infinitely many solutions if the lines are on top of each other, a unique intersection if they cross on all 3 axes, or they can just miss. This would be our example of no solutions. We'll see more of these examples in your homework. Good luck.